Hello everyone, I'm Yogendra Katarpo. I'm here to present a technique in cloud gaming environment which is Outatime, using speculation to enable low latency continuous interaction. Here are the authors and the key contributors of this paper. Let's talk about mobile games. As we all know, mobile games are very popular, accounting for nearly one third of the time spent on mobile devices. Many people actually play simple and basic graphic games such as Angry Bird, Fruit Ninja, and many others. It would be nice if all the smartphones are capable of playing high-end graphic games like the one that we play on Xbox or high-end PC games. But unfortunately, many devices have limited hardware capabilities. To remedy this problem, the cloud gaming has emerged where the client merely captures the user's input and sends that to the server over the network. All the computational expensive jobs happen in the server where the server performs the best game logic when there is a high quality graphics and sends back to the client over the network. The client merely just decodes that video stream. Companies like Nvidia, PlayStation and Sony OnLive have already started to provide gaming services on cloud. So here I have list of benefits and drawbacks of cloud gaming. Notice that the benefits of cloud gaming are very similar to the benefits of traditional cloud-based applications. Let me go through a couple of benefits. Every client can enjoy the high-end graphics provided by powerful server GPUs. This is especially appealing for the mobile devices such as basic laptops, phones, tablets, TVs, and other displays which lack high-end GPUs. Cloud games eases the developer pain, like platform compatibility headaches and platform specific performance tunings etc. are eliminated. Cloud gaming simplifies software deployment and management. Server management issues like bug fixes, software updates, hardware upgrades, content editions is far easier than modifying at client systems. And last, players can select from a vast library of games and instantly play any of them. Despite all these benefits, the cloud gaming also has some drawbacks. This paper mainly focused on network latency, which is very high in mobile networks and is not acceptable for the cloud gaming environment. If you don't have small enough latency, you can't have the high interactivity that you want to play for in cloud gaming. The majority of game applications are structured around the game loop, a repetitive execution of the following stages. Read user input, update the game state, and render display a frame. Each iteration of this loop is a logical tick of a game clock and corresponds to 32 milliseconds of a wall clock time for an effective frame rate of 30 frames per second. The time taken for one iteration of the game loop is a frame time. Actually, frame time is a key metric for assessing interactivity since it corresponds to the delay between the user input and the observed output. So let me go through a quick example on how cloud gaming would work in ideal scenario when there is no network latency. Here I have a server and a client and a game running at 30 FPS, each game time represented by T0, T1 and so on, approximately 32 milliseconds apart from each other. So at T0, client sends the input I0 to the server, and since there is no network latency, server receives it instantaneously, and upon receiving the input, server performs a processing and generates a frame F1 based on I0 and sends back to the client, which has to be displayed at time T1. Notice that here the server and client are working against deadline. Server needs to perform its processing job within 32 milliseconds window before the next user input arrives. Also, the client needs to display this generated frame within 32 milliseconds window. Although this is a nice scenario, let's be more realistic and add some network latency here, which is 128 millisecond, approximately 4 times of a time period. So the user input is delayed to the server. Instead of generating F1 at time T1, the client receives a frame F1 before T5. Basically here all the frames are delayed by 4 frames. So when this happens, lagging starts to occur in your game. For example, while playing a shooting game, you end up shooting your target continuously, but by the time bullet reaches the target would have already moved from that position. which is not acceptable. Unlike non-interactive video streaming, buffering is not possible for the interactive gaming. So, to tackle this inherent problem of high network latency that could be present in the mobile environment, this paper proposed a way to mitigate the latency via speculation execution. User studies have shown that players are sensitive to as little as 60 millisecond latency, but beyond this, it is not acceptable. So, the proposed solution is Outatime, a system that delivers real-time gaming interactivity as fast as traditional local client-side execution, despite latencies up to 256 milliseconds. Outertime's basic approach combines input prediction with speculative execution to render multiple possible frame outputs which could occur in RTT in the future. So let's look at an example. When the server receives the input I0 from the client, here it's going to be little bit different. The server receives it at time t2 as there is a latency. Then the server will look into what the user is going to do and then try to predict the user's most likely action to be in the future frames, and will generate the future frames based on the current input, noted that here as f'5. Then the f'5 frame will be sent to the client. Upon receiving the speculated frame, the client will do one of the two things. First, check if the server has made a perfect prediction. If it's good, the client will display f'5 frame as it is. Second, if the server makes misspeculation, the client has to do some state approximation at client level to handle this misprediction and show something that is closest to the expected state. By using this approach, user at the client level feels like its latest inputs get updated on the display almost instantaneously and the user don't perceive any delay. Here is an overview of Outatime system. In Outatime architecture, server and client does the traditional work done by other gaming client and servers, but it will also do additional work on top of it. Here is a list of standard jobs done by the gaming server and client, but Outatime will also do a couple of more things which are highlighted. First thing is that it does at the server level. It will perform speculation and also renders the speculated frame. And at the client level, there is a mechanism to handle misprediction. Here is an overview of Outatime architecture in detail. We'll discuss each of the highlighted boxes detail in coming slides. Let's focus on how speculation is performed. Speculation performance in Outatime depends upon being able to accurately predict future input and generate its corresponding output frames. So, the server needs to understand the user's input. If you think about it in real-time gaming scenario, at any given time, there are so many actions the user can take. So, there should be some sort of mechanism to predict actions. Here is a taxonomy of events. Input events are categorized into 3 categories, and different speculations are performed for each type of input event. Let me go through each of them. First thing is navigation events. These are basically move events like moving forward and backward, looking up and down, left, right. These are basically continuous and smooth type of actions. The second is impulse action. These happen generally at the user's will, such as firing a gun, casting a spell, and these events are inherently very bursty. And lastly, delay tolerant event. These are like opening a game menu, switch weapons, where the user don't care really if these actions are delayed by 120 millisecond latency, and it doesn't affect the game plan. So let's go through how speculation is performed for navigation events. Here is a small example, and we are running at 30 FPS and RTT at server level, let's say 256 millisecond latency. So we need to predict the user's action for next 8 inputs. For instance, input has received to the server at time t0 that the player moved to left and looked right for about 2 degrees. To answer the question what the user is going to do for the next 8 time ticks, super sampled Markov prediction model is used with training database on user traces. To construct a super sampled Markov model, we first pool the input device at a fast rate possible. This rate is dependent on the specific input device. For a 32 millisecond clock tick, we can often capture at least 4 samples per tick. Then the Markov model is constructed for navigation. The time is quantized with each discrete interval representing a game tick. The random variable navigation vector, capital NT, represent the change in 3D translation and rotation at time t. Each component here is quantized. Small nt represent an empirical navigation vector received from the client. Here the problem is to find the maximum likelihood estimator n cap of t plus lambda, where lambda is a RTT. Using the Markov model, the probability distribution of the navigation vector at the next step is dependent only upon the navigation vector from the current time step, p of nt plus 1 over capital NT. We predict the most likely navigation vector n cap of t plus 1 at the next time step as shown here. So how accurate is this prediction? Here we have a 5-dimensional navigation. As you can see, at the 64 millisecond latency, the above Markov prediction is actually good, as the accuracy is above 90% on all the 5-dimensional navigations. We can also see that as the network latency increases, the Markov prediction accuracy decreases. Mainly we should notice that the accuracy for the yaw angle prediction is really getting worse. This is because people actually tend to look left and right a lot in a Twitch based game application like Doom 3. And again, this is very independent accuracy. If we join this accuracy together, it's going to be worse accuracy. So definitely we need to have some mechanism to handle this misprediction. To refine Markov prediction, one of the two proposed ways has to be implemented depending on the severity of the error. We determine the expected error as a function of RTT from offline training. When errors are sufficiently low, typically corresponding to RTT less than 40 milliseconds, which is a threshold, an additional Kalman filter has to be applied to reduce the video shake. Otherwise, when RTT is greater than 40 milliseconds, misprediction compensation has to be used on the client to post-process the frame rendered by the server. Let's discuss on how to handle misprediction. When RTT is greater than 40 milliseconds, a noticeable fraction of navigation input is mispredicted, resulting in the users perceiving lack of control. So the goal in misprediction compensation is for the server to generate auxiliary view data f delta along its predicted frame, such that the client can reconstruct a new frame f double prime that is much better approximation of the desired frame f than f prime. This can be done using view interpolation, with which we can derive a novel camera viewpoint from a fixed number of initial cameras. View interpolation operates by having initial cameras capture depth information f delta in addition to two-dimensional RGB color information, which is f prime. It then interpolates to create a new two-dimensional image f double prime from f prime and f delta. So in this example shown here, a game Fable 3, the forward translation and left rotation is applied. The dog indicated by the green arrow is closer and towards the center after interpolation. For an effective interpolation, two requirements must be satisfied. First, the depth information must accurately reflect the three-dimensional scene. It is good that the graphics Z buffer precisely contains per pixel depth information and is already a byproduct of standard rendering. Second, the original two-dimensional scene must be sufficiently large so as to ensure that any interpolated view is bound with the original. To handle this case, instead of rendering a two-dimensional image by default, we render a cube map centered at the player's position. The cube map draws a panoramic 360-degree image on the 6 sides of a cube as shown in the figure. Using this, we can create any arbitrary viewpoint. But the problem here is the cube map's 6 faces are approximately 6 times the size of the original image. This cost is incurred at the multiple points in the system where data size is the main determinant of resource utilization, such as server rendering, encoding, bandwidth and decoding. People don't really tend to look up and down that much, actually spend more time looking at the left and right. Therefore, we render a clipped cube map rather than full cube map, which covers the more horizontal area and covers less vertical view to perform optimizations. The dotted line shown in the figure marks the clip region for an example rendering. So far, we discussed briefly how speculation happens for navigation events and how to compensate at the client level. Let's switch and understand impulse events. The objective for impulse speculation is to respond quickly to players' impulse input event while avoiding any visual inconsistencies. For example, in a first-person shooter, weapons should fire quickly when triggered, and enemies should not reappear shortly after dying. Therefore, a new speculation technique for impulse event is developed that differs substantially from navigation speculation rather than attempt to predict impulse events. Instead, we explore multiple outcomes in parallel. The server creates a speculative input sequence for all the possible events that may occur within one RTT, then executes each sequence and renders the final frame of each sequence and sends the set of speculative input sequences and frame pairs to the client. Upon receiving, the client chooses the event sequence that matches the events that actually happen and displays it to the corresponding frame. So let's look into an example. Here we have an impulse event timeline. At time t0, server is trying to predict what user is going to do in the next 8 time ticks. Let's focus on a fire event. At any game tick, the user can either fire or no fire. Binary choices. So if we explore all the possible states, the user actually will have 256 possible states, that is 2 power 8 choices, and it is not at all possible to speculate all possible branches. To remedy this problem, subsampling and time shifting mechanism is implemented. The main idea is that user is allowed to fire only at a specific time tick. In this example, user is allowed to fire at T3 and T7. So if the user triggers a fire event at T1 or T2, this event will be delayed until T3, which is shift forward. The reason to do so is, as per the user study, when there is an arbitrary delay of impulse event by 60 milliseconds, the users were unable to find the difference. So this works. But if the user fires at T4 and if the event is triggered at T7, which is the next window, this is going to be too much of latency and the user will be able to perceive the lagging effect, which we don't want to happen. So in this scenario, the nice thing is that since we are running speculation, we can actually go back in the time and treat as if the user fires it at T3, but in reality user fires it at T4. Using this approach, the authors were able to successfully narrow down the space from 256 choices to only 4 choices, and then the choices were sent to the client and the client chooses the right frame according to the user's input. While binary impulse events are most common, some games provide more options. For example, a Fable 3 player may cast a magic spell either directionally or unidirectionally, which is a ternary impulse event due to mutual exclusion. When a ternary or a quaternary impulse event happens, the state branching factor is 3 or 4 rather than 2 at every subsampling tick. So Outatime is able to support for an RTT less than 128 milliseconds of latency for ternary and quaternary impulse events without lowering the subsampling frequency. Next type of event is delay tolerant events. These events are slow relative to RTT. Delay tolerant events exhibit high cooldown times that exceeds 256 millisecond latency. Cooldown time is a period after an event is registered during which no other impulse events can be registered. For example, weapon loading in Doom 3 game takes anywhere from 1000 milliseconds to 2500 milliseconds. So whenever a delay tolerant input is activated at the client, it is okay to miss one full RTT of the events consequences as long as we can compress the time after the RTT. So far, we have seen how speculation works for different input events. Navigation and impulse speculation generate additional frames to transmit from server to client. As an example, consider impulse speculation, which for RTT of 256 milliseconds transmits 4 speculative frames for 4 possible worlds. Thus, the bandwidth overhead will be 4 times that of a transmitting a single frame. So, reduction in bandwidth is achieved by observing the frames from different speculations that share significant spatial and temporal similarity by joint encoding of speculative frames. Encoding is a server-side process of compressing raw RGB frames into a compact bit stream, which are then transmitted to the client where they are decoded and displayed. In Outatime, joint encoding is performed by extending the search process to be interspeculation. Macro blocks across different speculations are compared for equivalence. When an equivalency is found, we only need to transmit the data for the first macro block and use the pointers to it for the other macro blocks. To prototype Outatime, modifications were done for 2 action games. Doom 3, a Twitch-based gaming, is very sensitive to latency, and Fable 3, a role-playing game with fast action combat. While both the games are several years old, the core gameplay of first-person shooters and role-playing games, upon which Outatime dependencies, has not fundamentally changed in newer games. Doom 3 is a structured front-end executable known as a game engine and a content library. Doom 3 engine performs generic game routines such as capturing user input and rendering graphical content. Doom 3 content library involves everything specific for the game running on top of the engine. The content library is responsible for performing game-specific logic and handling the simulation of the game state. So, to support impulse speculation, the experiment spawned up to 4 Doom slaves, each of which is a modified instance of the original one. Each slave receives instructions from the master process regarding the speculation it should be executing and returns frame buffers as encoded bitstream packets to the master using shared memory. To support navigation speculation, a new additional slave command is added, which is render vi, which produces the cube map and depth maps necessary for interpolation. To perform speculation, Outatime uses checkpoint and restore to play forward a speculative sequence and roll back the sequence if it turns out to be incorrect. A combination of page level and object level checkpointing is used, which is unique among speculation systems. Both user studies and performance benchmarking were used to characterize the cost and benefits of Outatime. Outatime is tested against the following baselines. Standard FAT client consists of out-of-box Doom 3, which is a traditional client-only application. Standard thin client emulates the traditional cloud gaming architecture where Doom 3 is executed on a cloud server without speculation, and the player submits the input and views the output frames on a client. In user study, they were asked to provide a mean opinion score on the quality of a game, and the users were made to play with a thin client and Outatime at various RTTs. As per the user study, we can notice that as the network latency increases to 64 milliseconds, the MOS score for the thin client decreases significantly, and you can see here up to 400 millisecond latency. Outatime scores relatively high with the scores between 4 to 4.5 up through 256 millisecond latency and with a slight drop off at 384 milliseconds. Meanwhile, the people who played thin client have complained that the controls were very lag. Speculation imposes increased demand on resources, and bandwidth consumption is also 1.5 to 4.5 times higher than the standard cloud gaming depending on the RTT. Let's have a look on navigation event side by side comparison of responsiveness with thin client and with Outatime speculation. Notice the delay of baseline case on user's movement where the responsiveness is much better on Outatime. Now let's look at a case of triggering an in-game action event such as firing a weapon. Again, in baseline case, notice the delay of on-screen event and observe the improvement on Outatime. Finally, let's observe the overall effect on an action sequence. Note, from side by side, many shots actually miss their mark in the baseline case, whereas Outatime is very responsive by masking the network latency even for demand twitch interactions. In conclusion, Outatime can support up to 256 milliseconds of network latency, which enables cloud gaming providers to reach a much larger community while maintaining a high level of user experience. So, that's the end of our presentation. Thank you for watching.